Okay. Welcome, everyone, and thanks for coming to Can Journal Club this month. We're just going to give it a little 2 minutes to let folks join, and we'll get started just about a minute after the hour. Welcome, everyone who's just signing in. Thanks for joining the webinar today. We're just going to wait about another minute before we go ahead and get started with the session today. All right, welcome everyone. So it's about 1 minute after the hour. So we're going to go ahead and get started with the session for today. So I'm very pleased to be hosting my colleague, Jerry King. So the session today is titled The Importance of Solubility in Cannabis and Hemp Extraction, Processing, Product Formulation, and Packaging. So Jerry is here with us, and we'll get to the presentation very shortly. My name is Nigam Arora. I'm the Publication Committee Chair at CAN, and I will be moderating the session and helping with some Q&A at the end. So to share a little more about Jerry, he has over 57 years of experience in the field of chemistry, chemical engineering, and food technology. He has worked in government, industrial, academic, and consulting environments. Dr. King has published over 277 documents, including government reports, peer-reviewed publications, and he also holds 3 patents. He is world-renowned for his expertise and contributions to supercritical fluid CO2 technology in the fields of food, botanical and natural product processing, as well as contributions to analytical chemistry, material science, such as packaging coatings, surface modification, CO2-based cleanliness, and so on. So since 2003, Dr. King has had a focus on consulting, education, and R&D related to cannabis and hemp industries. So he is recognized multidisciplinary expert in the field of extraction, engineering, and chemistry, and particularly using critical fluid technology, and has made numerous presentations at science and engineering conferences. So Jerry's been involved with, excuse me, Dr. King. Sometimes I get I get a little too casual. I'm having fun. So Dr. King has been involved with CAN for several years. And he, in fact, is the recipient of the El Soli Award for Excellence in Cannabis Chemistry for this cycle. So we're excited to host him at the ACS National Meeting coming up in April as well. So just to share a few CAN announcements before we jump into the presentation. So next month we will be hosting Avery Gilbert, PhD, on March 25th. He'll be discussing cannabis terpenes, cultivar markers, aroma sources, or active ingredients is the title of that session. So we're excited for that. Also, there are several CAN sessions coming up at the spring 2021 ACS National Meeting. So, give and take with all these, pandemic things, but it is actually kind of nice. The ACS meeting this time around is fully online. There's reduced registration. I think the registration fee for members is as low as $99. So it's a really cool opportunity. I would encourage folks to sign up. I mean, there's programming across the board in so many great areas specific to cannabis. CAN will be hosting the sessions listed here, including Women in Cannabis, Advancements in Cannabis Analytical Chemistry. I'm hosting this one about cannabis-derived treatments for specific medical conditions. And then there'll also be some presentations about cannabis apart from cannabinoids. So what can cannabis be used for beyond, the stuff we commonly think about? So really excited for that. As we mentioned, El Soli Award is this award CAN does for excellence in cannabis chemistry. Dr. King is a recipient this time around. And if other folks would like to nominate people or submit, submissions for next year's award are open until July 1st, 2021. So please reach out if you're interested in that. And of course, if you're not already a CAN member, please join. We'd love to have you in the group. So I'd also like to thank our sponsors, Heidolf North America, Carbon Chemistry, CFS Consulting, which is in fact Jerry's, Dr. King's consulting company. So thank you for your support, Jerry, and also PerkinElmer. So really appreciate our sponsors as always. So before we get into the presentation itself, I just wanted to, Dr. King, ask you a few questions so the audience can get to know you a little bit. You and I share a little history. Do you want to tell everyone what our kind of commonality is?
Yeah, we both grew up and went to schools in Indianapolis, Indiana, in the state of Indiana. And I went to Butler University and got a BS and MS. I also ran on the track and field and cross country teams there. I believe you said, Nagim, that you were at IUPUI,
Yeah.
But we were a bit distant years apart as such. Beginning in maybe my late 20s after finishing my master's, I started to hit the road, so to speak, and went to the East Coast and was out there about 9 years working in industry and got my doctorate degree from Northeastern University in Back Bay, Boston. And then I came back to the Midwest after a brief stint in academia and worked in actually packaging research, which I'll talk a little bit about today, the connection. And then from 1986 to 2002, I went downstate to the USDA's National Center for Agricultural Research. And it really opened an opportunity for me to be very, very professionally active, including literally traveling all over the world. So that's kind of what got my name on the map, and I became recognized as someone with expertise in particularly supercritical extraction. But I worked in a number of other things, and as we were talking about, I ran a binary program consisting of process development and also analytical chemistry, namely to reduce the use of organic solvents in residue analysis for pesticides and other toxicants. So my PhD is originally in very physical analytical chemistry with a heavy bent on chromatography. I'll allude to that in the second slide. And then I had a brief stint at Los Alamos National Lab in northern New Mexico, and then very late in life, 62 I think it was, I became a faculty member in chemical engineering here at the University of Arkansas in Fayetteville. And in 2013, when I formally retired from there, I realized I wasn't going to retire because people started contacting me about the use of CO2, particularly in the cannabis and hemp field. So I've remained active in that, and it's afforded a lot of wonderful relationships and the ability to share my knowledge, and that's kind of what I'm hoping to do today.
That's so great. Well, thank you for sharing your story, Jerry. And just because I know there's you got a lot of meat in the presentation, and I know everyone's excited to see it. Let's go ahead and jump in. So I'm gonna stop sharing my screen here. Jerry, if you would please go ahead and share your presentation.
Okay. Uh, okay.
Perfect.
Okay.
All right. Well, thank you, Dr. King. Please take it away.
All right. I do have a lot to present. I may go over some things fairly quickly. I do have a lot of photographs, which I think are very illustrative, but we'll try to keep this to 50 to 60 minutes, give a little time for questions. Nigram has already told you about the title, and I won't repeat it here, but I'll go to the second slide, which sort of encapsulates what we just kind of went over. I have been in the CO2 extraction area, pressurized fluids extraction thing, starting in the chromatography area as far back as 1968. And then my PhD was in VARI, and I emphasize that physical analytical chemistry, particularly using chromatography as the fourth billet indicates there, in what we normally refer to as inverse chromatography, that is using chromatography to elicit physical chemical data of importance both in basic science like chemistry and also applied chemical engineering. And throughout this tenure of roughly 57 years, I have had the opportunity to work in government, in academia, at 2 different university positions, and then also in several industrial positions. And it's some of the industrial position background, and particularly the regulatory science experience I've had that dovetails with the food science experiences that I've had that I kind of want to bring into this talk. So it's going to include some things that I learned when I did R&D in polymer and coatings and packaging research, which I think are relevant to the cannabis and hemp space these days, or will be. So this seminar content, basically, yes, we're going to talk about extraction and processing, which I'm known for, and I hope that I haven't cut it too short, but I really wanted to come to the seminal area that I have a passion about, and I think that we need much more information and studies on, and that's solubility. The solubility of cannabinoids and terpenes and other associated compounds that we extract and process downstream. And it really also serves as a guide in the formulation of products. It's my own personal opinion that the formulation of products is done sort of semi-empirically, starting with kitchen chemistries about 30 to 40 years ago. And things like miscibility become very important, and I'll try to point out why I feel that's important. And then finally, I'll finish up with a role in the selection of packaging materials. I've got a little inset down there that says flux or permeation of things like cannabinoids and terpenes are kind of proportional to their solubility times their diffusion. And those 2 things really determine their flux or permeation. And that plays into not just extraction, but also, as I'll show you, into the packaging material. And I think that all these are sort of mixed in here. They each support one another, and particularly also how this kind of is going to play into what I see as an increasing level of regulation from the federal and state side in cannabis and hemp technology. So pure solutes, pure cannabinoids, pure terpenes. There are studies, and I'm most familiar with those done in liquid or supercritical CO2, but also I've had some experience in conventional liquid solvents like ethanol, which is very popular today in the hemp field. And what is surprising, it's getting a little better, is that in the field, we have so few actually documented studies. If you look up in a pharmacopoeia or a thing, and I was asked once in this consulting role about the temperature-dependent solubility of cannabinoids and ethanol, and discovered very quickly there was very, very little except something at 20 or 25 degrees centigrade that might give you so many milligrams per liter, something of that type. But what I have up here in the screen now is a very well documented study in the Journal of Supercritical Fluids that was done in cannabis-friendly Holland a number of years ago, and you can see it's on the solubility of tetrahydrocannabinol in CO2 under pressure. And also it included 3 or 4 other of the major cannabinoids. This is fine, but this is not real world because with the exception of isolate, if you wanted to extract that with CO2, we're really extracting complex mixtures from very natural product matrices like the cannabis strains, as well as the hemp strains too. So getting on with this data has been often cited. The important thing of it is I think it set the bar, that's a play on words, maybe a little bit too low, where we tend to use very low pressures, 200 to 300 bar max, in order to avoid the extraction of co-extracted unwanted materials, which usually we refer to as waxes, oils, and pigments that we have to do downstream processing to get rid of. And in order to avoid that, we try to be very specific, and there's some very good work going on. I see reports on it from several industrial laboratories. But the solubilities are very, very low, of the order of, as I show there, 3 times 10 to the minus 4 mole fraction. And that really doesn't translate into weight fraction solubilities of something of 1% or less. So one of the areas that I won't discuss is that back in time, I worked on this kind of research with a number of compounds and eventually worked at very, very high pressures. And there is a perception that, of course, the higher the pressure, the higher the capitalization costs for CO2 extraction. That's certainly true. But despite that, and despite this early research I was involved in, many of the solutes, the compounds that we extract with CO2, maximize at pressures of 700 bar or greater, and that's about 10,000 PSI in your pressure gauges. So people sort of, tend to dismiss this as not practical, but today we probably have 15 or more plants working worldwide at pressures approaching 1,000 atmospheres or 1,000 bar. And even at pressures a little bit higher is where the maximum solubility occurs for THC and CBD and carbon dioxide. So it's about equivalent to ethanol, but it requires those high pressures. So the reason in showing you this, and I think maybe you can see my cursor, maybe not, is that we have a way of determining these effective extraction parameters. And I say effective solubilities because they're really solubilities that are determined by running a timed increment of, say, CO2 or a subcritical fluid over your extraction bed of cannabis or hemp flower. And you measure the percent extracted, and this can be expressed in several ways. But the initial part of it is very linear with respect to volume and the time the extraction is conducted. And it's usually called the equilibrium controlled phase. And for a lot of materials, you'll get about 80% of theoretical yield there. And then you start to get into a time-dependent kinetic where diffusion is the domineering force. Well, in this linear portion here, you can effectively measure these, as I mentioned, effective solubilities, which are influenced by other materials you're extracting, like the co-solvent materials or co-solutes that I mentioned, the lipid materials, the waxes, etc. And I'm thankful. I spent 9 weeks in the early part of 2019 at Calian Innovation in New Zealand. One of the scientists I worked with was Teresa Marino, who has published this work again in the Journal of Supercritical Fluids. But they did some very fundamental studies, but also measuring effective solubilities in a particular type of hemp strain in this case. And you can see these yielded for the grams extract per grams of feed. So that's a dimensionless number. And likewise, if you plot it versus the kilograms of CO2 for every increment of time per kilogram of feed, hence a solvent to feed ratio, as it's referred to in chemical engineering lingo, you can see that these linear plots are very similar to the previous slide. And this allows you then to determine an effective solubility for all of the compounds you're extracting at these various increments as you conduct your extraction. And these were again done at fairly low densities, up to 300 bar. You can see in the little inset figures that Dr. Marino also took samples, and it shows the increasing pigmentation as you get sort of greedy on pressure and you get more and more of the unwanted type materials. So anyway, these are, two examples of how you can, do real world extractions. A number of years ago, in fact, 1968 was the earliest, I was introduced by a very famous guru in chromatography named J.C. Giddings. He's written some theoretical books that defined a lot of the fundamental principles of all forms of chromatography, what we know today as unified fluid chromatography. And in this work I did at the University of Utah in 1968, I was introduced to this concept called the Hildebrand solubility parameter. And I also had worked previously a little bit on its utilization in the paint and coatings industry, which is really where it comes out of. And a very forward development in this field called the Hansen solubility parameter, or HSP for short, was developed by a Danish person doing his doctorate degrees named Charles Hansen. I've had the opportunity to co-author a paper with him. And essentially what the solubility parameter says is you have an internal energy in your cannabinoid and you have a certain molar volume. And that defines essentially the square root or the solubility parameter that is characteristic of how it behaves as a solute or a solvent, in the case, for example, of dissolving something in it. It can also be looked at in this three-dimensional HSP concept, and it's divided into dispersion, D, and polar components, and also hydrogen bonding solubility parameter. Well, when you have a pressurized fluid, or any fluid, it can be a condensed fluid like a liquid solvent, this empirical equation called the Giddings-Hildebrand solubility parameter, shown in light blue there, allowed you, using reduced state parameters from corresponding states theory, to relate the solubility parameter to the square root of the critical pressure of the fluid. For CO2, that would be 72 atmospheres. And then the ratio of reduced pressures of the fluid under various extraction or experimental conditions to its ultimate compression as a liquid, which typically runs at a reduced pressure rho sub R somewhere between 2.7 and 3.2. Perhaps the most important thing to take away from this is that when the fluid solubility parameter equals that of the solute, the terpene, the cannabinoid, wax, or whatever you're extracting here, like dissolves like, and you get the maximum solubility. What it doesn't mean is you can have miscibility, where the difference between the fluid solubility and the solute, if it's within, say, 5 roughly megapascal at the half power, there's also the older units called Hildebrand units there, which you can get by dividing by 2. You also have miscibility. It just isn't at the maximum solubility. And so this forms sort of a parabola of expressing solubility, which allows you to maximize it in liquid solvent use or in sub or supercritical use. And it also allows you to see where you're going to have to be to get some kind of minimum miscibility in this case. And this here is how the solubility parameter of carbon dioxide varies with pressure and temperature, at least for the given ranges here that are expressed here. And you can see that there's an enormous increase in the solubility parameter for about the first 17 megapascals or 170 bars. And then you start to see a further increase, but it sort of asymptotes off at all temperatures. And actually very far out here is where you need to be to reach your maximum solubility with a number of solutes. Temperature also helps because usually the vapor pressures increase. And this is all very well known for many, many solutes. And there have been many studies in academic and government labs, some industrial, that bear out this solubility relationship. And all fluids will follow this. When you use subcritical CO2, you don't have quite the advantage of the variability in pressure. You're locked into varying the density of the CO2 and by temperature, and that's very helpful when you're doing terpene extraction. I simply put this up here. It's a very good paper done by a research team at Complutense University in Madrid, Spain, which uses this Hansen solubility theory to explain, in this case, the high value fatty acids from a particular botanical species in this case. And it's a good paper. It's available online too, or in the Hansen website, which I'll say something about at the end of the talk. This is very interesting. I had an interface with a gentleman from Cool Clean. They build what I like to refer to as more of a sort of a basket cleaning device using liquid CO2. It's very effective the way it's done, but it's sort of like a washing machine. It was initially developed for dry cleaning using carbon dioxide. And he took the expressions for these contributions to the solubility parameter, the delta D, the delta P, and the delta H that are in the literature, and essentially used this to compare them on a plot of reduced state, which you'll see here in a minute. Here you see the total Hildebrand solubility parameter on the vertical axis versus the pressure in megapascals here. And the point in looking at this was that if you looked at the subcritical condition, in this case, he picked 293, which I believe is about 20 degrees centigrade. Could you get equivalent solubility parameters in the liquid CO2 state corresponding to what you could do in the supercritical state? And this is shown here, and he termed it, his name was Nelson Sorbo. I acknowledge him at the end of the talk here, that this represented a solubility saddle. And as you can see from the sort of cross arrows here, you can get the same solubility parameter, roughly about 14 in both the subcritical state as the same you can get at the supercritical state at about 11 or 12 megapascals, but a higher temperature, certainly. So it shows you that it is, possible to do certain things with liquid carbon dioxide just as effective as with supercritical CO2. Now, we have developed a very handy program and also have canvassed the literature now for many decades. I will mention particularly the gentleman who developed this Excel program to determine solubility parameters, particularly for liquids that are used in extraction, like liquid butane, heptane in some cases back in time. And again, the candidates that we just talked about, liquid CO2 and supercritical CO2. And also liquid ethanol, which has come on gangbusters, particularly in the hemp field. And I also present here some solubility parameters that we've calculated from group contribution methods and also the HSP method that we developed the Excel program from for other materials that are used as, say, vape additives like glycerol, water, which I'll explain later that we have an interest in because it has a very, very high solubility parameter, and things that are lipophilic, like the things you would use to make canna butters or olive oil infusions and so forth. And the F and T means simply that some of these fluids, they can have their solubility parameter varied as indicated as either a function of temperature or also a function of temperature and pressure. So we've developed quite, a literature or listing of these. This is just simply a continuation here, particularly of what are typical waxes that are found in cannabinoids. Also, chlorophyll is here. Lecithin and phosphatidylcholine are there with their temperature functional dependencies. These were determined by technique I have a lot of experience in called inverse gas chromatography. And of course, these are used particularly in emulsification schemes to make cannabinoids somewhat aqueous soluble. And then you see 4 examples of the acid forms of THC, CBD, and the solubility parameters calculated by this methodology, which I'm going to explain a little better. And then just a couple of typical prominent terpenes that are used in the various cannabis strains are found in them. And of course, you'll notice that most of the terpenes have much lower solubility parameters than the cannabinoids. So I was very fortunate to have, and he may be listening in California, a very ambitious graduate student and also a postdoc for a year and a half named Kirthi Srinivas. And Kirthi helped develop a method for calculating solubility parameters from dissecting essentially the molecular structure of cannabinoids and terpenes. And he did this for, as you can see, several of the acid forms listed here. In fact, you can do it for about any cannabinoid you want that you have the molecular structure to. And he also compared these with another group contribution method called the Fedor's method. The agreement was excellent, actually. And that's kind of what you see in the colored things here, a comparison between the 2 methods. And these, again, were done at, ambient 25 degrees centigrade conditions. So we also did, of course, many of the neutral cannabinoids like CBN, THC, and CBD. Again, I always forget to say this, but the numbers in the first set here are done under the Hildebrand units, and the ones that are practically twice the value here the ones below are in the megapascal 1/2 units that are more the convention these days. But you'll find these solubility parameters in the literature listed both ways, particularly if you go back in time. So Dr. Srinivas, anyway, was developed this very novel program, and we widely applied it to many different kinds of structures and so forth. And we think, as I hope to illustrate here shortly, that it's very helpful to rationalize things in the extraction field, also in making formulations or understanding why maybe they don't work so well, and also giving a rationalization to what happens in certain packaging situations. And this just happens to be a repeat of the same thing I mentioned for the cannabinoids, solutes, or compounds. This is done for about a dozen of the major terpenes found in many of the cannabis flowers and hemp flowers. Beta-caryophyllene particularly is there on the end, which I know is of interest certainly in the hemp area. We then did a comparison, and this has been presented at other conferences. And to be frank about it, I don't want to spend a lot of time in it because it's a little bit old hat, but we essentially listed these cannabinoid solubility parameters for several of these major cannabinoids, and also, as you can see here, some of the major terps here. And we also then listed the solvents into 2 categories, one that covered some unusual solvents like dimethyl ether, propane and butane are here in this nested around here, and also tetrafluoroethane. And then over here, it's pretty much CO2, both in the liquid state and also at various pressures and temperatures in the supercritical state. So again, where they overlap here with these solvents, with the solutes, these are the maximum conditions. As you can see, with these materials, particularly like propane and butane, are excellent for retaining, getting the terpenes extracted out of these biomasses. We also can do this with CO2. And ethanol is also a very effective solvent. As you decrease the temperature in ethanol, it gains more cohesional energy density, so it increases. But even at room temperature conditions, it's very effective for solubilizing the cannabinoids, as happens in the real world. And you can actually do extractions at 1,000 bar and 40 degrees centigrade and maximize the solubility of THC. That's based on theory. The waxes, the triglyceride oils, and chlorophyll, they come out intermediately. And that's why you can't get too carried away with pressure when you're doing things like CO2 extraction. Also, ethanol will bring these over and require sub-ambient precipitation to avoid having the chlorophyll and the waxes in that. So this is a plot based on data taken in the sub and supercritical region for ethanol, and it shows, again, the relationship between the solubility parameter, the temperature in degrees Kelvin, and the pressure in megapascal. And this is a critical point right here. And I show this because I'm going to then relate it to a real world example. And the real world example is the comparison of the solubility parameter of CBD, terps, and waxes with ethanol as a function of temperature. And what this shows, if you can read the codes down here for the various solutes, cannabidiol was of particular interest here, some of the terpenes, also the typical wax kind of components that would also be co-extracted, and then ethanol here, which you see in the dashed line here, that we can tune the temperature to do the selective extraction of the cannabinoid compounds. And so this allows us, you know, to somewhat precipitate in ethanol the unwanted type components, and that CBD can be better extracted at both ambient and higher temperature, while some of these other ones then can be precipitated at lower temperatures. I was fortunate enough in 2019 to work with a very ambitious capstone senior design engineering team at the University of Alberta in Canada. And when I was there, they did quite a bit of literature searching, because one of the problems in developing process engineering concepts is you need physical data for modeling or to do your economic calculations and processing. And many times that's lacking. You have to either resort to theoretical predictions, which can be kind of flaky at times, but they were able to find some interesting data. And then using best fit Excel programs show that the solubility for like ethanol and waxes could be predicted. And as you can see how low the solubility dips here based on extrapolating the best fit here, an exponential function, you know, you're getting here at zero, almost beyond zero here, negligible solubility, which agrees with theory. You also have here the solubility of a typical lipid like stearic acid, and it shows the same trend. Again, based on quite a bit of data here, it can exponentially be best fitted. And again, it's very, very low solubility here at the lower temperatures. Likewise, this is a fit for chlorophyll. They were able to find some temperature dependent data here between roughly 30 and 60 degrees centigrade. And again, you can see the chlorophyll solubility is very low, but it doesn't take much chlorophyll in there to change the color of the resultant extract. So this just shows you that, you know, where you have data available, you can model it and use it in engineering calculations. So I want to be conscientious of the time here. They then proceeded to do molar solubilities of the cannabinoids and ethanol at 25 degrees centigrade. And they used something called the sort of the HSP distance, which is a result of what we call the Hildebrand sphere. You're going to see a couple of these in a minute. And it allowed them to plot the log of the molar solubility versus the HSP distance using ethanol as the central point at room temperature, 25 degrees centigrade. And what was interesting is that using this relationship, they were able to confirm that the actual solubility is the single point solubility at 25 degrees centigrade in ethanol in milligrams per mil was accurate. And that was very gratifying. It was just unfortunate we didn't have more temperature dependent data on the solubility. So using these extrapolated data for ethanol Hansen solubility parameters, we can determine by, as a function of temperature, what the solubility parameter is for ethanol. And this sets us up to then compare it with the solubility parameters of the cannabinoids and the other compounds that are found typically in cannabis or hemp extracts. This is simply a breakdown showing the calculation of the Hansen parameters for ethanol water mixtures. So we can do mixtures too. And this just shows you industrial grades of ethanol that go between 85 and 100 weight percent in this case. And you see the total ones, probably not that many significant figures over there. So this is an enormous flexibility, and I don't expect you to read this, but from Excel spreadsheets, you can see we can do all the cannabinoids over here as a function of percent ethanol as we go to higher purity grades of ethanol, and also as a function of temperature. In this case, this is showing the temperature between 25 centigrade clear out to minus 80. Another concept that's dependent on these solubility parameters are activity coefficients. And this gets into solution thermodynamics, and I don't want to bore you with a lot of theory, but this is going to be of interest in just a little bit. The log of the activity coefficients are equal to what we call the chi interaction parameters, and the total value here is equal to an enthalpic or thermal component plus the log of the entropic activity coefficient. Usually this is ignored and very small, except in the case of very high polymer and very low molecular weight solutes, like terpenes would be an example. So if we assume that this gamma S is equal to 0, then the thermal activity coefficient becomes the dominating factor. And having these other parameters, essentially when we look at the activity coefficient or the escaping tendency, in this case, it's the difference between the two solubility parameters of the cannabinoid in the case of the solute and your solvent, be it a super or subcritical gas, or it could be a liquid solvent in this case. So we've applied this to several cases that occur in using these compressed fluids and liquid solvents. And what's interesting, I'll just point out a couple of them, is here you have THC and THC CO2 at two different pressures and 40 degrees centigrade. Here you're almost having an ideal solution, maximum miscibility, solubility. Here you have some solubility, but it's not high. And that's in agreement with what we see in the laboratory and the processing stage. In the case of ethanol, in this case, it's very interesting for THC here. You get very finite things which are considering the closeness of the solubility parameter of ethanol with THC and the other cannabinoids isn't surprising. On the other hand, if you go down to minus 80 degrees centigrade, in this case, the waxes which you want to precipitate out have enormous activity coefficients, which means waxes don't like to stay in cold ethanol. And so they have enormous exponential terms. Same thing with the terpenes. This also dispels a mythology that the loss of terpenes when you're doing ethanol extraction is due primarily to the fact they have these hideous activity coefficients in cold ethanol. They don't like ethanol, period, at whatever temperature. So anyway, it shows that the CO2 and particularly the butane, particularly at very ambient conditions, are very good solvents, and they have very good activity coefficients. So we use the butane solubility parameter equation here, the temperature and the pressure, and that's what the critical loci look like, the surface response plot, to look at what happens when you have THCA, the so-called diamonds, when you're doing butane extraction, and how terpenes and wax is extracted in this case. And again, you see the relative solubility parameters plotted here versus temperature clear down to almost minus 80 in this case. And this was very interesting because what it was able to tell us is that after you finish the butane extraction and you let it, and you can see the liquid butane would be volatilizing off, you have a number of co-extractives that come with it. And if you wait in time, you can precipitate them. And what you see here is the diamonds or the THCA precipitating. And this is simply due to the fact that THCA minus the solubility parameter butane is a fairly large difference, and it accounts for a very large activity coefficient. And the reason why this immiscibility isn't experienced in real time is that you're also co-extracting a lot of other co-extractions here. So again, I'm looking at the time here. This is the RAD equation that is based on the Hildebrand solubility parameter theory. And essentially, it is essentially spheroids, or in the ideal case, essentially a sphere that shows that the differences between the various dispersion and polar and hydrogen bonding components of both the solvent and the solute, i.e. the cannabinoid, the terpene, that these can be expressed in this way, and that there's an RAD distance that when it equals unity, you're at the maximum solubility. So all of these have sort of a circular like fashion, depending on how their ordinates and abscissas are expressed. This was looking at Glycerol-Solute systems because we were kind of interested, and I'll show you in a minute, given the enormous difference between glycerol and also a solute like a cannabinoid or a terpene. And I'm going to blow this up in a minute, but glycerol is used frequently as an adjuvant in vaping compositions. We determined the glycerol solubility parameter from inverse GC, and we also compared it with literature values, which correspondingly checked okay. And what this shows you here is that for many of the solutes, and you see for beta-caryophyllene, the acid forms, the CBD, THC, and the neutral forms, that the dark triangles indicate that they're insoluble in glycerol. So depending on how you're formulating your vape liquid, what you're adding in the formulation in this case, and this is a little bit out of sequence here, you have these RADs all greater than unity, which means they're not in the soluble zone of the sphere. And what this translates into real life is that here you have a glycerol, essentially vape insert at 200 milligrams per mil of CBD. And it also is crystallized here. And the reason it's crystallized is that it's not miscible. There's too much glycerol in there to affect the solubility. So the way, as it says in the instructions, you get by this is by warming it up before you vape using this. But it's a good example of how this theory can be used to predict the immiscibility or precipitation in this case. And again, it's because CBD is 23 megapascals to the half hour, and glycerol is quite much higher. Now let's go to a little bit about formulation. I'm going to do this very, very quickly. We have many different kinds of formulated products. You know, chocolates are one, and I make sure I want to say something about the anomalous analytical results that come in analyzing chocolates, particularly lower values than are actually on the label. And what people don't appreciate in, I think, formulation area, and that I've been fortunate to pass through, being in a very lipid-rich environment at the USDA lab there in Peoria, Illinois, that I mentioned previously, is that when you look at a chocolate or you look at something like olive oil or palm oil that are used, you know, in a lot of infused products, they have a, I'll call it a non-homogeneity based upon different phase diagrams. For instance, they can show a certain amount of amorphous behavior or crystalline behavior. And so these phase diagrams here, and if you're interested, you can read this article, simply talk about solid state miscibility of these triacetyl glycerol crystals that would form something like maybe in palm oil or something of that type. And so what I don't think formulators realize is that when you take a sample or you're trying to infuse a product in this lipid matrix here, it's likely not going to be homogeneous. And that also has implications when you take samples to try to analyze them. And this is just another thing I included since this is going to be posted probably on YouTube for cocoa butter and triasterin mixtures that support the same thing. So we have all these complex debris, and I'm going to go through this very fast, all sorts of products. And this brings me again to sort of the mixture of formulating and also how we package our formulations in this case, but primarily for, as I finish up here, packaging. So this is very interesting. These are vape concentrate containers. The bottom is glass, which is good. The top is plastic with liners, which I'll show you may not be so good. All sorts of, I will call semi-crude type of packaging is used. This is your typical, plastic sealant thing here. And what the whole thing I'm coming to say, as you'll see shortly, is that the loss of terpenes and loss of cannabinoids into these packaging materials can be substantial. Here are gummy bears. All of the components, the gummy bears are mixed in with this very high sugar matrix, in this case, things like dextrin, sucrose, some citric acid too. But all of the surrounding thing are made of plastic. They are almost like natural sinks for the terpenes and to some degree the cannabinoids. This is a sample I bought in Oregon when I visited a hemp farm. It was a lavender massage oil, and it sat around on a sink. And as I touched it after a number of weeks, it was greasy on the outside. And it became very apparent to me, and also the odor, that the lavender components and the CBD were coming right through the package, that this choice of the packaging plastic was not adequate. And you can look at all these things, such as the CBD hard candies. These shatter jars, again, are all plastic here, all of them, including liners. Likewise, these are all plastic. Syringe here, here's a CBD vaping liquid. There's no consideration given to the fact that maybe these aren't the best packaging materials in terms of retention over time of the cannabinoids and the terpene components. And that affects why, when you analyze them, they don't have necessarily what they say on the label. So since I worked in the food industry, I drew up this analogy of a PET, polyethylene terephthalate bottle. And what you see here in this case is the PET, when it's filled with a Coke, the usual concern in the food industry and the Food and Drug Administration, is the whole sector that does this, is our polymer adjuvants or oligomers from the PET migrating into the cola thing, or wherever PET is used, interfaced with the food, or adjuvants such as phthalates and so forth. We're going to look at a little bit the reverse situation in just a moment. So the packaging of food, is done to maximize, with ideal packaging, things like the sealing characteristics, reducing the permeation in this case, and also the migration, particularly the migration of these additives, impurities, and breakdown products. For instance, a breakdown product of PET can be ethylene glycol, which is toxic. So most of the things in the cannabis industry, what we've been concerned with so far is making them child resistant. Of course, the advertising and marketing is important, and also the labeling as required by state or mainly state laws these days. But there is a problem with this, and there is an area that has now been studied for several years called the scalping of flavors in packaged foods. And that is where things are migrating from what is in the package, the bottle, the plastic container, whatever it may be, and they are actually permeating and going into the packaging material, like the PET bottle in this case. And so what you're doing is you're losing things like your terpenes and your cannabinoids, and there's a thermodynamic reason for that, particularly an extreme in the case where you have nanoemulsions that you have formed in water, which aren't stable. They're false solubilities. Anyway, so depending on your food matrix, whether it's lipophilic, vegetable oil, medium chain triglycerides, MCTs, chocolates, all these have different cohesive energy densities. So you've already seen some of the lipophilic oils in the tables I presented. You haven't seen so much of the glassy sugars that constitute the gummies, and even honeys have been infused with cannabinoids. But these are such high solubility parameter, cohesional energy densities, that there is very little true solubility of cannabinoids or terpenes in this. And so even though you can mechanically mix these in your cooking kitchens or whatever, in time they will migrate out to the surface and perhaps into the actual packaging. And the water content, I'll illustrate that later, but for the time being will mean that. And there are also polymeric matrices like chewing gums that are starch-based that are also very high cohesive energy densities. And essentially what you have are two-phase systems with your cannabinoids and your terpenes associating with themselves. They're just mechanically mixed in with this. So as you look at more things, and again, I'm running short on time here, this is a rock candy, which I bought the other day in the dispensary here in Fayetteville, Arkansas. And it's a CBD isolate that's infused into this rock candy. The minute I opened this, without opening the thing, I could smell the terpenes and the effect of the CBD extract here. They were coming right through the all plastic container here. This is a similar case of hemp gummies that are in an all plastic container. Likewise, here you see with syringe, for various applications, all plastic here, whether they're THC or CBD laden. This is one in particular I took apart here because what you have here is three components in this stopper. You have a neoprene or rubber polybutadiene material here. You also have a plastic here. You also have a sealing ring, which is polymeric. And surprisingly, this is not glass. It is actually a polymeric material. So with all of these various polymeric constituents, and you'll see a few of them in a minute in their solubility parameters, it isn't surprising to me when you're using these kind of packaging concepts that you're going to lose cannabinoids and terps. I put this here because it just shows all these solubility parameters that were expressed in other tables previously, but you didn't have water. Notice that water is about 47 or 48 megapascal solubility parameter, and that's much, much higher than any of the cannabinoids, any of the terps, and also the lipophilic and most of the extraction solvents. Even ethanol and glycerol are lower. So when you get a nanoemulsified type of material where they've gone to extreme care to form these microscopic, I'll call them nanoscopic micelles in this case, by using certain surfactants and so forth, what you have is an unstable condition. In time, these will begin to cloud up. And so most of them have shelf lives as such. So it's really sort of a false solubility because there's no way that you can have, based on the thermodynamic concept, cannabinoids and terpenes having high solubilities in water. And this is, of course, the technique. I don't have the time to go into it, but there's a lot of expertise out there in forming these nanoemulsions. These are the solubility parameters of polymers. And here you see PET at the top. You see the polyolefins like PP and high-density polyethylene, polystyrene. You also see the neoprene or rubber polybutadiene, and you see nylon, which frequently gets used in in certain cannabis containers. Then you look at the cannabidiol value, 23 here, and you look at water. Well, given the activity coefficient differences that we showed predict for the higher, what I call the lower activity coefficients close to unity, it's obvious that cannabidiol in water is going to want to go into these polymeric materials rather than stay in the water. So that's the thermodynamic basis of the salting out, as it might be referred to, of these materials from the water matrices in this case. It also suggests why, if you run an analysis, that you won't find some of your cannabinoids or CBD there because it's already migrated into the polymer matrix. Finally, I've had an interest because I am in ballroom dancing and I deal with instructors who have pain occasionally from dance instruction in what are called transdermal patches. I'll show you a picture of one in a minute. And these actually operate on the idea that the actual polymer containing the drug is inside a adhesive layer, which you peel back, and then you have a backing layer. You'll see one of them peel back, and then this is what interfaces with your skin in these various formats here. And by the way, the solubility parameter of human skin is, depending on what values you quote, between 20 and 24 megapascal and a half. The reason why it's been determined is that people wear protective gloves. They've had to determine the solubility parameter of skin. So this is a typical pure ratios transdermal patch, CBD at a stated value here. And a very good reference I've given here, it's really worth it. It employs the solubility parameter, but here you have your transdermal patch and your alcoholic wipe here. And this is what it looks like on the side. Your drug, your CBD is impregnated there. This is what it looks like when you take it apart. You can see again, there's some kind of polymeric matrix that's laced with the CBD, and this is the adhesive patch. And this is just a close-up view of it in this case. And these usually can last from anywhere from 1 day to 4 days in this case. So as I kind of finish up here, I thought you might find a couple of these things of interest here. This is a citrus CBD transdermal patch, like the CBD that's derived in this case from hemp. What caught my eye about this, it's one of the very few that actually had a label indicating that it used an acrylic adhesive and some kind of polymer blend. Again, they're trying to protect their intellectual property here. But more interesting was the CBD in this case was derived from citrus peels. And CBD has been cited to be in citrus peels, so this was not a hemp-derived product. Another thing you have to be careful of in packaging is the presence of possibly reactive conditions. There was in the annual meeting last year a paper by a group in Michigan at a university that talked about the effect of citric acid in gummy bear products on degrading cannabinoids. This simply shows here we have CBD and citric acid here in a bath bomb. But the same thing applies to CBD-infused candies, such as your gummy bears and the type of things here. So the citric acid, even though it's a weak acid, can convert the CBD or the THC. And finally, as I finish off here, I thought you might find this interesting. This is a actual sustainable hemp package made from hemp fiber. And this company is using it to contain an actual hemp flower in this case. And I find that interesting that it's hemp on hemp, so to speak. I've listed a couple of interesting publications here that you might like to follow up on. One, if you're interested in the properties of water in the sub and critical state, including room temperature conditions. This is one by the postdoc former grad student that I mentioned, Kirsi Srinivas. These are the solubility parameters for subcritical water. I believe, since I've got your ear here, that subcritical water at higher temperatures can be used to essentially degrade hemp waste and turn it into potentially chemicals or at least a biofuel source. And finally, I would like to acknowledge several of the people I've mentioned here. Kirsi Srinivas, who's with Blue Nalu out in San Diego now. Dr. Marino, who I work with at Callahan Innovation. The very prolific Capstone Senior Design Team 7 at the University of Alberta produced a 482-page process report comparing the economics of essentially hemp extraction and CBD using ethanol versus CO2, and Dr. Sorbel at Cool Clean. And again, I have a website that has some of this work documented and some of the things I've said. It's still a work in progress, but I invite you to visit it. And again, I'd like to express my gratitude to NIGAM and the CAN people for allowing me to give this webinar. And also, I trust you found it of interest. Unfortunately, I didn't list my email, but I can certainly provide it. I have a presence on Facebook and also LinkedIn that you can connect with me. But thank you again for your attention. It's been an honor to address you via this webinar.
Thank you so much, Dr. King. We really enjoyed the presentation. And do you just want to let people know what is your preferred email? And I can put that in the chat box if that's helpful.
Yeah, it's a lowercase K-I-N-G, King, J-W, 100. So it's King JW100 at hotmail.com. I apologize.
No problem. I think, Jerry, just to confirm, kingjw100 at hotmail.com, right?
Correct.
Okay, great. So if anyone wants to get in touch with Dr. King, I just pinged his email into the chat. So feel free. We have about a little 5-10 minutes here to go over some questions. If you have any follow-ups, please reach out to Dr. King directly. So just to jump in, we did get some questions from the audience. So as I said, we have about 10 minutes here, so we'll get as many as we can in. So the first one is asking, how would you calculate the Hansen solubility parameters for terpenes and cannabinoids for supercritical extraction?
We did them by this Excel program. Essentially, that's one program. There are others by group incremental, essentially approaches. There are several methods, but what this allowed us to do is to have increments of the energy for, say, a methyl group or a hydroxyl group, which has a much higher cohesive energy density. Then we have respective molar volumes for these functional groups. So it's sort of like in organic chemistry. You're taking the material things apart, you're summing them up and dividing them and taking the square root. And this can be done for both the three-dimensional solubility parameter as well as the historic Hildebrand parameters. There are a number of these group contribution things. What you really would like to do, and this is where we're lacking so much of the data, is to determine these by other methods. And there are experimental methods. I hadn't had the time to go into them. One of the things I'm very much wanting to do is to use what I call inverse gas chromatography to determine the solubility parameter of CBD as a function of temperature. That would be very valuable to have in use of the theory and product formulations too, where you're heating CBD a bit too. And that's just something I haven't gotten around to doing yet, but there are experimental ways of determining these. The thing that amazes me, other than the essential oil literature being a source of terpene solubility data, like in CO2, you can find a fair amount of terpene solubility data that's coming from lemon oil or whatever the essential oil would be and its components that's extrapolatable or convertible into the cannabis space, but not so much so for cannabinoids, besides that one study.
So as a follow-up, are there any publications that outline that method to calculate those solubility parameters? Are there resources that folks can go out and find, or is this stuff that they need to develop?
Well, I gave one early on. I don't know whether my screen's still active.
It is, yeah. Feel free to take us back, yeah.
This one is a good one to look at. There's also one by the group at Computensa that is in about the third or fourth slide. I won't go through all of them. And there are others. You know, if you do a simple Google search, solubility parameter dash supercritical fluid, my guess would be you'll probably find 50 or more publications and various applications, including a certain niche of them that are in the area. One of the papers that I went over it very quickly that was in a pharmaceutical journal calculates all the solubility parameters for a sustained delivery of a drug. Let's see if I can bring it up real quick here, which I think would interest product formulators a great deal because these people are not coming from the extraction arena. They are coming from That's way in front here, a different thing. But this paper was a treasure trove of, and it's available online too. You can easily download it. It's one of the MPI things. Where is it? But this is the one in that's very good from Computensa, and then the one that dealt with the sustained delivery, the sort of patch type thing, is can't find it now. But if you'll contact me, I'll refer you to it. Okay.
Yeah, so yeah, and just thank you, Dr. King, and just to reiterate,
There it is. There it is. Yeah.
Oh, perfect, perfect,
Right
perfect.
there it is.
So, and just to share,
paper.
I'm sorry, go ahead, go ahead.
No, what it deals with is essentially the topical administration of cannabidiol and the fluence of vehicle-related aspects. These are the additives like the glycols and the other materials to assist in the skin permeation process. And it's in this journal, Pharmaceuticals. There is another one that I didn't list here too, that is in an epilepsy journal that deals with solubility parameters in some kind of application in a formulation to treat Dravet syndrome.
Excellent. So, and just to share with the audience, as with all our Journal Club presentations, this will make its way up onto the CAN Journal Club YouTube page. Sometimes it takes us, a few weeks or so, but we'll get it up there. So feel free to refer back to it. And then when you follow Dr. King's advice and you Google it, and there's 50 publications, and you want to know which one to really read, you can email Dr. King, and I'm sure he'll help out. So. Great. Well, appreciate the input there. And we have a few other questions. So let me see. Here's one. How does the composition of the cannabis or hemp affect the CO2 extraction process?
Oh, I think it definitely has an effect. In other words, it is somewhat strain dependent. One of the things that surprised me, I know one company out in Oregon that does this for different purposes. We had an active program at the USDA that involved developing very small scale extractors for analytical chemistry purposes that can also be used as screening extractors, like to screen your various hemp strains. So if you're a toll refiner and you're getting different field crops and different strains of, say, marijuana or cannabis in, that you want to see how they extract, and you can extrapolate that to your larger scale up conditions using these smaller scale extractors where you might use 10 cc's or 50 cc's before you load up a 50-liter vessel can be very instructive, because no extraction curve is going to be the same for one strain versus another, or one type of flower versus another. And it's also dependent on the preparation of the hemp or the cannabis biomass, things such as moisture and co-extractives. I can't help but emphasize that co-extractives are going to have an effect on how much CBD and THCA and the cannabinoids come into. Even the terpenes interact, not in the way you normally think of it, the entourage effect, but sort of in the extraction. They're sort of an entourage effect in the extraction. So if you had simply powdered isolate CBD and you did a CO2 extraction, if you tried to extrapolate those conditions to a certain strain of CBD and a hemp, strain, Fermion or whatever some of the names are, you would find that the two aren't exactly corresponding. You would have some headway by knowing the CBD solubility in CO2 like the Dutch study showed, but your other compounds you're co-extracting are also either assisting or maybe negatively affecting the extraction of the cannabinoids. Usually they assist it. They kind of are internal co-solvents.
And thank you for all that info. Just as a follow-up, are there any kind of modeling programs or like ability to predict this ahead of time? Like, how are people approaching this so that when they have strain X versus strain Y, that they know what parameters to use when they start their extraction run?
Well, from my consulting, and this involves some consulting also with companies building, I call it these push button screen extractors. They try to develop, you know, an algorithm that is typical of the one I showed, you know, early on. It usually has a linear portion and then an asymptotes, you know. One thing you can do that isn't oftentimes done is, as shown by the study at Marino and colleagues, that the people here, is that if you do these generalized coordinates here, you actually have where you have the solvent to feed ratio here and the grams of extract versus the grams of feed on a dry basis, or that's essentially your feed factor, what you put into the extractor. This will give you a good idea of how to scale up. However, these slopes and everything may differ. So when we go here, the slope for a certain strain, it may not be quite the same for a second strain, you know. So most of what your companies that have algorithms to model this, and, you know, really hemp or cannabis with its unique structure with the terps, and everything. There has been a lot of sophisticated modeling done in other botanical materials like vegetable oils or essential oils and other botanicals. But to my knowledge, nobody has taken on the gigantic task of doing cannabis. You know, it's sort of very, very difficult, as complex as cannabis is with all the compounds, and also its morphology or its spatial thing as a plant. We're also, you know, comminuting this and grinding it up, you know, to make the extraction more effective, to essentially sharpen this. If we had an ideal extraction here, it would have a very, very sharp thing and a very quick transition into diffusion control. That's what you would like to have, and that's what you like to have by particularly operating at higher pressures or densities, and also doing fine grinding and comminution.
And I'm sure, you know, I appreciate what you're saying about the complexity of the plant, it being a challenge with cannabis. Hopefully, you know, later today you'll get an email in your inbox with someone saying they want to do that project with you, right? What a fun project to do. So
most people who don't have licenses to do model extractions for customers would be an example. They like to use hops, you know, but that isn't quite the same. Hops frequently, what's now today done, all hops worldwide is done by supercritical CO2. Doesn't matter where you are in the world. It used to be frequently, or was at one time, done with subcritical CO2, but the supercritical CO2 is a faster method. And generally, this is fed in as granular materials in the big scale plants that do it. I wish I'd shown a picture of a big scale plant that does hops. In Yakima, Washington is the world sort of center, at least the US Center for Hops Extraction. They have huge facilities there. But hops is frequently used by a lot of the companies selling equipment to demonstrate they can do. But you couldn't use an extraction curve like this for hops and necessarily extrapolate it to a cannabis strain.
yeah, that makes sense. And so just for time's sake, I'm going to combine a couple of these final questions and seek your commentary. So you had shared with us some of these issues with packaging, with stability, with the gummies, with the consistency in the product. So let me see if I can combine these two questions and kind of pose them to you. So one question is about the, or let me just read this. Given what you said about the migratory nature and instability of cannabinoids in gummies or candy, how should they be packaged for maximum safety and efficacy? I think efficacy meaning down the road when someone consumes them, right? The other question correlated is, have you ever seen on-package stability data? So what the audience wants to know is, what's the best method to make these things uniform and stable and later on efficacious? And then have you seen any folks demonstrating that they know that and putting it on their packaging?
First of all, there's hardly anything currently NIGOM, except that one case I showed you where the cannabinoids were coming from orange peels, where that has, been required information. And I think that's going to change. When the Food and Drug Administration takes over monitoring a lot of the cannabis things, they have a whole sector that deals with the packaging. A few years back, I was involved in this research heavily. There are all sorts of packaging materials. I'm trying to bring up something here very quickly. But all these polymers, there's a whole, this is just a small sector of their solubility parameters. So if I had cannabidiol here at 23.8, and I wanted, excuse me, something that it would not be miscible with, I would try to pick something with a solubility parameter. Well, here's where it gets difficult. When you have it in a gummy bear or a high starch or a high sugar carbohydrate matrix here, or this is true with water, eventually it's going to phase segregate is what I call it. It's going to rise to the surface. And particularly with the terpenes that might be associated with or any flavoring type agent that might be added along, they are then going to want to go to a less polar, a smaller solubility parameter environment. So what I didn't do a particularly good job is here you have cannabidiol, and it may be sitting in a starch or a polar polymer that I'm going to say is going to be something like 30 or 40 megapascals, and I may be incorrect on that. So it's going to go by activity coefficients to a more favorable environment that it wants to be in. And it turns out many of these polymers offer that. Now, as I look at it here and I see 23, a good environment it would like to go to would be nylon. And that's used in a lot of closure seals that I've seen. PET in this case, and again, you don't know because unless they have the stamp for recycling, like PP and the triangle in this case, you don't know. They're not declaring the polymeric material that's being used. I think that's going to be required in the future, particularly in recycling, possibly. But right now, essentially, these compounds are all going to favor migration of these polymers, and the relative values of the polymer solubility parameters are probably going to determine the degree of migration. Again, this is a back migration. You also have the possibility of migration. Some of these polymers have trace amounts of adjuvants into your cannabis material. It wouldn't shock me to find a phthalate or some kind of oligomer like from PET in your cannabis material, whether it's an infused product or even a liquid. The worst case I can think of is water down here, because as eventually the nanoemulsions, start to decay, if that's the right term, and they're going to flee the water and they're going to, be absorbed by the polymeric matrix.
Totally. So, yeah, really, go ahead.
We have solubility parameters and things like cellulose where you roll, we have all these synthetic polymers and we also have polylactide, biodegradable polymers. All these have solubility parameters that have been determined. Another way of determining them is by this inverse chromatography technique that I mentioned. And most of them have been determined that way, by the way.
Totally. Well, Dr. King, thank you so much for answering all these questions and for your presentation. Again, anyone who wants to speak further with Dr. King, please do see his email in the chat, kingjw100@hotmail.com. Just I wanted to call that out because I'm going to close the Zoom here in a minute, and I want to make sure anyone can grab it. So with that, go ahead.
I'll add it to the front of my presentation too, so they have it.
Yeah.
Okay.
Perfect. Yeah. So with that, thank you again, Dr. King, and thank you to all the attendees, to our sponsors, and we look forward to seeing everyone next month.
Thank you again. Bye.
All right. Take care, all.